Note, even though the net work done by all the forces on the backpack is 0, the hiker does do work on the backpack equal to 1,470 joules. What the? I'll give you work. What's up, Fizzlords? We're back in Japan, as you can tell from the Vendo, or Jido Hanbaiki as they call them. They're everywhere and often standing awkwardly in a really nice photo. Now listen, I've been reading the first year My Experience reports and I've seen you all complaining. Wow, all this normal force stuff, it's all so complicated. Well, buckle up folks, I've got the ticket out of that hellscape. It's time for Lagrangian mechanics. Let's get started. Okay, so the basic idea, I like to call it the lazy walker problem. And it's really nicely demonstrated by this photograph here. Humans are lazy, they want to get from point A to point B with the least amount of effort and in the shortest amount of time. And often what happens is there's sort of a wrong path to do that. Often that's the one that some clown has built because it looks architecturally nice or follows a fence or something like that. And then there's the rational human's path that it evolves into that is sort of the correct path that everyone wants to follow to minimize the amount of time it takes or the amount of effort it takes to get from one point to another. Lagrangian mechanics is basically the same idea, except what we're trying to do here is minimize a thing that we call action, and we'll talk a little bit about that in a moment. So, just to motivate this just a tiny bit more, imagine you're a dynamical system. You can imagine it's just being this ball and you want to get from point A to point B. It could be just projectile motion, okay? Often what you want to do in problems is know the starting position and then be able to predict what the ending position is. Or you might know what the ending position is and want to work out backwards what the starting position was. Imagine you get bombed and you want to work out where the bomb came from. And often what's really useful to know is actually the path that happens in between, which is a whole series of points all the way from point A to point B. And so you can imagine a problem where rather than just fire the ball from this location and get it to land in that location, the problem is something along the lines of how do I get it from this location here to this location here via a circular hoop that's up in the air, and where do I have to put that hoop in order to intercept the path so that it goes through the hoop like that rather than go over the top or smash into it and fall down onto the ground, okay? So what we often really care about is not just point A and point B, but paths. And the question becomes, how do you actually work out what the path that nature chooses? Because as you'll know from first year courses, it's a parabola if you're firing a projectile, but what's to say it's not up, across, and downwards, okay? And so this is the kind of physical principle we're trying to get at with Lagrangian mechanics. So we have a thing that we call action, and it's a new quantity I'm going to define today, and what we're going to do is start out with kinetic energy, which you've all seen before. It's half the mass times the velocity squared, and a potential energy. And I've been calling it U today, I'm going to call it V. I'm going to mix it up and jumble between the two from lecture to lecture, depending what my favorite letter for the day is, okay? Alright, so let's start just by considering this in one dimension, just to keep things nice and simple, so dealing with a problem just in X. And of course we can scale this up later to 3 dimensions and multiple particles in a problem and so forth, work our way from there. So we define this thing called the action of a trajectory. Taylor calls it S, I'd like to call it A, so I'm going to call it A. And it's basically the integral from T0, which is the starting position, to T1, which is the ending position that you're interested in. So it's the two ends of the motion. And so what we're interested in is trying to find what path it takes from one of those points to the other. So every single possible path we consider in these types of problems always passes through these two endpoints, okay? And what we do is we integrate this quantity here, t minus v, okay? And if we put this in, we get something that looks a little bit like this. It's a half mx dot squared minus v of x. Okay, so the first question you're probably going to have is, why is it t minus v? Wouldn't it be t plus v, right? T plus v is the total energy of the system. Surely that's the thing that means something. No, it's definitely a minus. You can try it for yourselves as an exercise with a plus later with some of the problems, and you'll find out that you actually get the wrong answer. Okay, so it really is t minus v. Your second question is probably, why is the action given by this at all? And the answer basically is the same as many problems in physics, because it works. Okay. We'll show in a lot of detail in later lectures that it really does work, both by getting it as an outcome of calculus and by demonstrating problems with it. But the aim today is to give you a really quick introduction to the concept and how it works, and maybe deal with a couple of really simple problems for this. And then we're going to go off and do some other topics for a few lectures, just to let this settle into your mind and get used to the idea. And then we're going to come back and we're going to hit it hard, right? We'll do really rigorous mathematical treatment of the whole thing and some very complicated problems where the power of this approach really demonstrates itself. Okay. So, to take this one step further, we define the term inside that integral as a thing that we call a Lagrangian L. So L is basically t minus v. And what we're always doing in Lagrangian mechanics is basically looking at the action as the integral of the Lagrangian over the path. Okay? And this Lagrangian L will be a function of position and velocities, right? So you'll always get a velocity term from your kinetic energy. Your potential usually carries a position term, but it can carry other things as well. And it can also be a function of time, okay? We'll see that later on in the course. Okay, so if we think back to this question at the start about the lazy walker problem and trying to minimize the amount of effort and time it takes to get from point A to point B, what happens with Lagrangian mechanics and physical problems is basically the path is chosen such that it minimizes the action. And what we'll see later on is doesn't necessarily need to be a minimum, it just needs to be stationary in the sense that the first derivative is equal to 0. But for the moment, we'll consider it least because it's the easiest case, and it's also the case that happens most often. So we call this the principle of least action. Some people call it Hamilton's principle, and we'll call it that later in the course. And the idea is that whatever path is ultimately the correct path for the particle taking the motion is basically the path that minimizes the action. Okay. Now, one thing to keep in mind here is the integral A is looking at the Lagrangian, which is a function of position and velocity at that particular point, and it's adding it up because of the integral over the entire path, okay? So really the action is not a function of just a few variables. The Lagrangian's a function of a few variables, but the action is not just the function of a few variables, but it's a function of an infinite number of variables because it contains all the coordinates at every instant of time in the problem. So really, you can imagine this almost like a compression algorithm. What we do is we take all the coordinates for the entire path, and we basically stuff them into this one little equation that's an integral of a function of really simple set of things. Okay, so the trajectory itself is a function, and later on in lectures 7 and 8, we'll treat it as a function. And that makes a function of a function, and that's something we call a functional in physics and mathematics. And minimizing a functional is something that's a little bit more complicated than just minimizing a function. And this is something we deal with in lecture 7 when we talk about calculus of variations. I'm not going to get into that today, but we'll do this formally in a later lecture. Okay. All right. So this first half, what I'm going to do is sink quite a bit of time into deriving something that we call the Euler-Lagrange equation. And we're going to do it for a single degree of freedom. And at the moment, I'm just going to state it. It basically says that the time derivative of the partial derivative of the Lagrangian with respect to x dot minus the partial derivative of the Lagrangian with respect to x is equal to 0. Okay? We'll derive it here. We'll take a break. And then in the second half, I'll come back and we'll do a couple of examples and pull a couple of key points out. And the idea today is just to set a prelude. We'll do a lot of this in much more rigorous fashion in lectures 7, 8, and 9. Okay? All right. So, pulling together this derivation. This is one of the few pieces in this course that I actually take from Susskind's book. So if you have the book and you're reading it, you'll find this in there. It's a little bit of a clanger in Susskind's book. In addition to a pretty egregious typo running through the algebra for this, there's a point that he comes to where he basically skips what I consider to be at least a dozen steps that are not quite simple and straightforward to do. So if you're going to try and do this directly from the book without running through the path that I'm taking here, you're possibly in for a little bit of pain. But I'm going to break it down, right down into little bit of pieces and do every step along the way here, just so that we're really clear on the problem, okay? Now, the way we're going to approach this is as a discretization problem. So it's a little bit different to the way we're going to do it in the calculus of variations in lecture 7. And the thing is, when we do it the calculus of variations route, it's very easy to miss what's going on. And so what we're going to do here today is a little bit more cumbersome, but the point is for you to really see what we're doing with this mathematical apparatus to get this, so that later on when we do it in a more elegant fashion, you can kind of see what the underpinning background is for it, okay? Okay, so we're going to do this by discretizing the problem. So let's draw this up just so it's really clear. What we would have is our normal continuous problem that we're interested in. And so what we have is some position t0 and some time t0, some time t1, some position x0, some position x1. And we're interested in, so this is x as a function of time, and we're interested in the path that we take in getting from one to the other. So imagine you have this nice little simple snaky path between the two. What we're going to do in taking this to be discrete is we're still going to have our times and our positions here, and we're still going to have our beginning point and our end point, right? T0, T1, X0, X1. But what we're going to do is chop our path into little segments delta t, where delta t is bigger than 0. Okay, so we're going to go from dt being an infinitesimal in integrating over the path to a delta t that's is non-infinitesimal. So you can imagine our path being a set of little steps in here, each of which we can divide up into some little amount of time delta t. Okay, this is just basic discretization. If we blow this up a little bit, the way I'm going to approach this problem is to focus on just two segments of this little path and how I can minimize the action by moving just one of the common points in that segment. Okay, so let's draw this up. This is maybe I'll get straighter lines here because this needs to be drawn well. Okay, so we've still got x along here, still got t along there, right? And now we're going to deal with tn minus 1, tn, and tn plus 1. So we're basically going to chop this path up into a very large number of pieces, big N, and we're going to look at the nth piece along the way. And so we're going to have points at these things, just here. And then we can call these xn plus 1, xn, and xn minus 1. Like so, okay? And when you discretize a curve, basically what you do is you chop it up into linear segments that run up against each other. So you can imagine there's a linear segment that comes in here. We've got a straight line that goes between those 2 points. We've got a straight line that goes between those 2 points, and a dotted line that goes in up here, okay? And this is what we often call a linear interpolation. We basically just take out the curve, and if the gaps between the places are small enough, all your straight lines, segments become small enough, you don't see them, and you get your curve back when you look at it from a distance, okay? All right, so when we do a linear interpolation, we're actually considering what is the midpoint of this. And each of these lines that we have in here will also have a slope, okay? So if we look at this one up on the top right, the midpoint, and let's call it xn plus as a function of t, is going to be x xn plus xn plus 1 divided by 2, okay? So really all it is it's just the, you've got the high point, you've got the low point, you take the average, and that's where the center is, okay? It's just a midpoint equation. And then the other thing that this segment of line has is a slope. And that slope is given by n, let's call it xn plus dot. And I'm using this notation xn plus to indicate that we're n, and not just, we're not at n plus 1, we're just a little bit beyond n, so that's n plus, okay? You know at UNSW we love adding plus to everything, so we'll add plus to this as well. Okay, so this is going to be xn plus 1 minus xn on t. Actually, it's delta t, because it's a small change in time between those 2 points. So we've got basically a delta t is tn plus 1 minus tn. Okay, so we've chopped that problem up into all these nice little bits and pieces, and you can imagine there's a whole pile of these. And now what we do is we basically go backwards from an integral to a sum. Okay, you've done this in all your calculus courses. So basically what we'd be doing is taking L dt and turning it back into a sum of L over these little increments delta t, where we have we add them all up, and each point we've got a gradient and a midpoint, and we just work our way along this curve in all its segments, okay? So now what we can do is recast our action integral from being an integral that looks like this, a equals integral t naught t1 L x dot x dt, and we can turn it into something instead that looks like this. A equals sum over n of L n plus x dot n plus x n plus delta t. Okay, so what we're doing is just working our way through calculating all the little segments, and on each little segment there's a Lagrangian at the n plus point that has coordinates x dot n plus and x n plus. Okay, so we can take this one step further and write this as sum over n L x n minus n plus 1 minus x n on delta t, so that's our x dot, and x n plus x n plus 1 over 2 delta t. Okay, we've got this. Now, what we want to do is minimize that thing. Okay, so what we're going to do is, what we would normally do there is take the derivative and make it equal to 0. Okay, and in reality, what you would do is every single point that joins these segments together is flexible. You can move it around, and you would move them each individually and mutually until you find the point where that derivative becomes zero. Okay, that's going to be a really complicated thing to do with this approach, but what I can do is, you can imagine I sort of do a halfway minimization. So I leave most of my points in place, and I just take one and I just move it around and see what it does and see if I can find the place where it minimizes the action. Okay, and the best way to do this is just to choose a specific point and work on it. So we're going to choose a specific point, and let's choose my favorite number from when I was a kid, 8. So we're going to deal with point number 8, right? So what our action now looks like is a whole pile of terms up to 8. Then there's L of x8 minus x7 on delta t, comma x7 plus x8 on 2 delta t, plus there's not going to be enough room there, so I'm going to put it down here. L x9 minus x8 on delta t, x8 plus x9 on 2 delta t, and a whole pile of terms above it, right, all the way up to n. So we basically just isolated 2 of the terms that we care about at the moment, because they're the ones that are connected to point 8. Point 8 connects to point 9 on its right, and it connects to point 7 on its left, and so 9 and 7 are fixed points. But if we move 8, what we're going to do is change the slope of this segment and where its midpoint is, and we're going to change the slope of this segment and where its midpoint is. So we have to care about the changes of those 2 midpoints on either side of point 8. So 8 plus and 8 minus are the 2 that we really care about here. Okay? All right. So what we're now going to do to minimize A, and you'll spot that this is not strictly minimizing A, because all we're really doing is setting the derivative to 0, and you know that that can be a minimum, it can be a maximum, it can even be an inflection point. In most cases it's a minimum, it's not always, and we'll talk about some examples of that later on, but we'll just talk about minimization because it sort of keeps things simple here. So if we want to minimize A, what we're really saying here is that we want dA with respect to whatever change we make, and we would call it, say, dx, to be equal to 0. Okay, and here, because the only thing that we're changing in x is x8, we're going to call this d on dx8, and we'll make it a partial derivative because our action could depend on a whole pile of points in here, and it's not just one that we're worried about. Okay, all right. I'm going to try to be as rigorous as possible with my notation here. There has to be a little bit of wiggle on it, but we'll see how we go. Okay. All right. So now when we take the derivative with respect to x8, something really nice happens. There's only 2 terms in that big string of terms that depend on x8, and that's the 2 terms that we just wrote in the notes down there. So all the other terms have no dependence on x8 at all, and so when you take the derivative, they all vanish. Okay, it's a really nice aspect of this problem. So if we write dA on dx8, we've now only got 2 terms, and those 2 terms are d on dx8 of L x8 minus x7 on delta t, comma x7 plus x8 on 2 delta t, plus L x9 minus x8 on delta t, x8 plus x9 on 2 delta t. And that's all that's left, right? All the other terms go to 0, and what we can do is we can pull this term off, and let's call it A, and we can pull this term off here, and let's call it B, and we can deal with these 2 things separately, right? This is really good exam technique for, it's always nice in lecture courses to think about aspects of lectures that become nice technique for for exams, and this is one of them. You don't want to write big strings of equations again and again and again. The best thing is to just pull the pieces apart, deal with the pieces, and reassemble it later on when you've got everything sorted out. Okay. So we're going to go through a little chain of logic here, and we'll do it for A. It applies just as well from A to B, except there's one little thing that happens when we do it with B, and then we'll build it back together again, get our final answer, and take ourselves a break. Okay, so one thing we're going to need here is the chain rule, and ultimately it comes from Jacobian matrices in real analysis. I'm not going to derive it here because that's what maths courses are for, but I'm going to put down an expression for what it looks like just so we've got something to work with, right? So what we're going to say here is that dl, and it's a function of x and x, because of course x dot is a function of x, on dx at some position, and of course you will done these sorts of things, the chain rule at a position in your real analysis course, hopefully. This will be dl on dx at x equals x naught, dx on dx at x equals x naught, plus dl on df at x equals x naught, df on dx at x equals x naught. Okay, so this is basically just breaking up a function of a function. That's what chain rule is. Derivative of a function into some partials that we can do on our way through. And so now what we're going to do is apply this just to our little term up above here, A. So we're just going to look at what happens to the 7/8 segment due to a move in 8. And we know that the 9/8 segment due to a move in 8 is kind of going to be similar with a little tiny little twist to it. Okay. All right, so our term A looks like this: d on dx8 L x dot 7 plus x 7 plus delta t. So that's the first part, and I'm going to skip down to the next line to write this because I need a little bit of space. So it's going to be dl on dx 7 plus at x 7 plus times dx 7 plus on dx 8 at x 7 plus dl on dx 7 plus dot at x 7 plus times dx 7 plus on dx 8 at x 7 plus. And then this all needs to be in brackets, and we need to carry our delta t on the end, okay? All right, so basically all I've done is just taken that expression for function rule, for chain rule, and plugged in what I have, and I've broken it up into pieces, right? And I've had to be a little sort of, how do I number things 7 plus? Why is it 7 plus and not 8, and so forth? That's a little tricky. You kind of have to think about where things are happening and where it affects things. But if you trawl back through this once it's finished and compare it to the graph that I had at the start, this graph up here, and work your way through the logic, you'll probably see why I'm calling the various things the things that they are. Okay, so the notation's a little clunky, but what's going to ultimately happen is that we would take delta t and make it go to 0. Or infinitesimally close to 0 to get our dt back, and when we get that 7 plus is not much different to 8 is not much different to 8 plus, and so really what we call things in here doesn't matter enormously in the differential limit. Okay. All right, so we've got two derivatives that we need to work out here that are really important, right? The first one is we need to work out what dx 7 plus on dx 8 is. And it's going to be d on dx 8 of x7 plus x8 on 2. And if we take the derivative of that with respect to x8, we would just get a half, right? And so this thing is a half. The other one we have to worry about here is dx dot 7 plus on dx8. And it is d on dx8 of x8 minus x7 on delta t. And of course, now we have a term in x8 and a term in x7, and the x7 one disappears, and what we get out of here is 1 on delta t. Okay? And those of you who are able to think really clearly ahead will probably spot what's going to be different about the x9, x8 term already, right? There's something coming up here. So we can rebuild this thing back together, and so our term A becomes a half dl on dx8 at x7 plus. And we're going to leave that alone for the moment because it's kind of a difficult thing to deal with and it doesn't really help us very much in dealing with this problem. And then we've got 1 over delta t dl on dx8 dot at x7 plus delta t. Okay? Nice and easy. Okay, so I'm not going to redo this all for B because it's going to get kind of boring. I'm just going to point out the really important points when it comes to B. Okay, so let's deal with B. The really important point when it comes to B is now when we look at dx8 plus dot on dx8, okay, which is the corresponding term to the one just up here. It's now going to be d on dx8 of x9 minus x8 on delta t. And if we take this thing, now our x8 has a minus sign in front of it, so what we get out of this derivative is minus 1 over delta t, okay? Now if you do that with the midpoint term, because there's a plus in the midpoint term, it's positive x8 in both cases, so it's still a half. The sign change only comes on this second term in B, and it's a really important sign change, which is why I want to highlight it. So then what we get as our expression for B, if we would wrap all this up, would be something that looks like a half dl on dx8 at x8 plus. And this is where you've got to be careful. It's not a plus, it's a minus 1 on delta t dl on dx8 dot at x8 plus delta t. All right, so you notice we've got the same thing for A and B here. Except for a minus sign in the middle, and that minus sign is really crucial. So what we can do now is go back to our dA on dx8, and what we can do is write it not by clustering the terms in terms of the one that's at 7 plus and the one that's at 8 plus, but we can cluster the terms in terms of the 2 midpoint terms and the 2 slope terms, right? So what we would end up with here is something that looks like this: a half dl on dx8 at x7 plus dl on dx8 at x8 plus minus 1 on delta t, and this is where Susskind has his typo. He hasn't accounted for his delta t's properly in here, so if you go back to that book, what I've got down here will not match what's in the book from a couple of lines back, simply because he's dropped a term in it. And even in his YouTube video, he drops the same term. And then I think in the YouTube video, he actually picks it back up halfway, but definitely in the book it's missed. You can't catch it easily and fix when you've got book copies all over the world. So dl on dx, let me write that properly. dl on dx8 dot at 8 plus minus dl on dx 8 dot at x7 plus. Okay, and I need a delta t on the end. This whole thing is going to be in brackets, and it's going to have a little delta t on the end. Okay. All right. So if you have a look at my detailed notes on the website, you'll notice that I've actually skipped a step from that. So you can go back and see it. Basically what I've done is just reverse the order of 7 plus and 8 plus in the second half of this equation so that I get it set up the way I want, right? This is why the signs work out the way they do. If you think about what these two components are, this component on the left just here is a midpoint. And it's a midpoint at our position x8, right? Because it's x7 plus on one side, x8 plus on the other, and so we're back in the midpoint again. So if you think your way back up to this graph that we had earlier where we talked about midpoints, we had this is our point 7 plus, this is our point 8 plus, and then this in here, you could imagine having a midpoint line in here, and the midpoint of that midpoint line would be 8, right? Really nice feature of discretized problems is that sometimes you jump from one set of points back to the other, back to the other, back to the other, and you can do some really clever tricks with that. Okay, so we can take this bit here, and this bit here is now a slope, and it's a slope at x8 in much the same way. It's the slope between x7 plus and x8 plus, and that slope will be at the position x8, right? So what we've really done by doing this problem is get dA on dx8 at position x8, right? Okay, so because we know what these things are in here, this thing is just dl on dx8, and this is just d on dt of dl on dx8 dot. So what we've got over here on the left here is a midpoint, so it's going to be the same thing that we had, dl on dx8. And then over here on the right, what we've got is dl on dx8, and we're taking the slope of it, and it's the slope with respect to t, so that's why we get this d on dt out the front. So what we're going to do is take that derivative now dA on, let me just move up a bit. That derivative dA on dx8 is dl on dx8 minus d on dt dl on dx dot 8 delta t, and we need to make this thing 0, okay? There's two ways this can become 0. One is delta t is 0. It's not a very good idea because the problem basically disappears, right? It's essentially the same thing as just making the whole problem vanish. What you would do with this problem is take delta t and make it go dt, and that means it becomes infinitesimally small, but infinitesimally small is strictly not 0, okay? So we can also say that delta t can't be 0 because we're going back to the differential limit, and that means we're not going back to 0. So the other term has to be 0. This one here has to be 0. And that means basically we've got this thing, dl on dx8 minus d on dt, dl dx8 dot has to be equal to 0. Now you'll notice what we did, that will minimize the action, but all we changed is 1 point, and what we really could have done, we could have done 0.7, we could have done 0.9, we could have done 0.2, we could have done 0.10,036, or we could have done all the points, right? So really the 8 doesn't matter very much, and what we can actually do is just drop it and generalize this equation as a thing across the whole thing, okay? And so when we generalize this thing, out pops what we call the Euler-Lagrange equation. And that's the nice thing we've got in the slide. just here, and so it's a little bit of a detailed path to getting it out, but in the end you can kind of see why this thing exists, right? Basically what we do is we just try to tweak our path until we minimize the action, and when we minimize the action we find that this thing holds, and so what we end up doing is basically going, well, if this thing holds when the action is minimized, what we should do is make this equation work, and then that should by default minimize the action. So we use the Euler-Lagrange equation as a way to work out what the least action scenario is. Okay? All right. Let's take a short break, and then in the next half of the lecture I'll go through some examples of how this gets used just to demonstrate the idea.